Please make sure you have your copy of the assignment assessment review titration, which is more sour. In this review experiment, we're going to ask the question, which of these two lemonade powder drinks contains more of the sour flavor ingredient citric acid? You might wonder, where do I get the ideas for these experiments? Well, usually it's by just going grocery shopping, or maybe 5 in the morning I'm walking the aisles of Pick and Save, or this time I was at Walmart after school and I saw lemonade powder, 2 different brands. I wondered which one was more sour. Now in lab we can't do taste tests because we can't drink or eat things in lab, so we can use chemistry to find out by titration. But before we do that, let's just review how the titration strategy works. So suppose I have a cup, and in this cup I have a sample of acid in a mixture. Suppose that we think of that like it's a cliff, and we want to find out where the end of the cliff is by walking up towards the edge of the cliff by taking steps. Now the steps that we're going to take are steps of potassium hydroxide, a solution that we're adding 1 milliliter at a time. Each time we add a milliliter of the solution to the cup, what we're doing is we're using up some of the acid that's in the cup, so that brings us closer to the edge of the cliff that we're trying to find. Each 1 milliliter of the solution contains 0.010 grams of potassium hydroxide, 1/100th of a gram that we can measure very accurately and precisely, more so than if we were trying to add it by adding a solid. This time the solid is dissolved in the solution. Now, how do we know when all the acid is gone? When you're adding the steps, each step you take brings you closer to the edge of the cliff until there's no more acid. Now, when there's no more acid, there's something else that's in the mixture that will react with the potassium hydroxide, and that's phenolphthalein, a color change indicator. It turns pink. So after we've reached the edge of the cliff, the next step you take, there's no more cliff, so the next potassium hydroxide that you add reacts with phenolphthalein and turns the solution pink. If you know how many milliliters of this you added, then you know how many grams you added. And if you know how many grams of one thing there are in a chemical reaction, then you can figure out how many grams of the other thing it took to react with it. So what we're going to do in the experiment is we're going to titrate cups of the lemonade powder mixed with water, the same strength as if you were going to prepare it at home and drink it. So I have a sample of 20 milliliters of the Great Value mixture and 20 milliliters of the Crystal Light mixture, and to each one I'm adding 5 drops of the phenolphthalein, our color change indicator. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then I'm going to add 1 milliliter at a time of the potassium hydroxide solution until the solution turns pink and stays pink. So if I do this one first, add 1 milliliter, and then add another milliliter. And as I mix it, I'm looking for it to turn pink and to stay pink. Check back in a minute and I'll show you how the results turned out. Okay, I was adding the potassium hydroxide solution 1 milliliter at a time, and so for the Crystal Light it took 11 milliliters of this potassium hydroxide to use up all of the citric acid that was in this sample. And for the other brand, for the Great Value brand, it took only 8 milliliters to use up the citric acid that was in the mixture. So let's calculate how many grams of citric acid then are in each of the 2 different brands. Okay, I'll record my data on the front of the assignment. For the Crystal Light titration, it took 12 milliliters, and for the Great Value titration, it took 8 milliliters. Now, for each of these 12 milliliters, if there's 1/100th of a gram of potassium hydroxide, if I multiply, then that means that there's 0.12 grams of potassium hydroxide in that titration trial. And for the Great Value titration, it's 0.08 grams of potassium hydroxide. I need to know how much it took to do the titration so that in my calculations on the back, I can figure out how much citric acid there was in each. Let's do the calculations. So we want to find out how much citric acid is in each sample that was tested. We need to know the molar mass of the citric acid for our calculations. So looking at the formula for citric acid, I'll list the elements, hydrogen, carbon, and oxygen, and then I'll count how many of each there are. I see 8 hydrogens in the formula and 6 carbons, and 7 oxygens. And then using the periodic table, I'll find their atomic mass. Hydrogen is 1 atomic mass unit, carbon is 12 atomic mass units, and oxygen is 16 atomic mass units. Multiply, and then, I can't do that one in my head. Get the calculator out. 7 times 16, 112. And then add those together. Let's see, 112 plus 72 plus 8 is 192. So each 1 mole of citric acid is 192 grams of citric acid. The reason that we use the mole is so that we can count things in chemistry. We count them by weighing them. If we know how much it weighs or what its mass is, then we can say how many molecules of citric acid there were by grouping them in moles. Let's look at the actual problem that we're going to do. How much citric acid is in each sample? The citric acid is the thing that we're trying to find out. So in our solving strategy, we're going to call that Y. It's why we're doing the problem. So everywhere in the solving strategy you see Y, it will be citric acid. We need to know about the citric acid, what is its coefficient in a balanced reaction equation. In our reaction equation here, there's just 1 citric acid. There's no number in front, so that means that there's just 1 of them. The presence of the formula counts itself. The potassium hydroxide that we added is the X. It's the thing that we know, what we're going to start with. So everywhere in the solving strategy you see X, it will be potassium hydroxide. And we need to know what is its coefficient in the balanced reaction equation. It's 3. So for every 1 citric acid that was in the mixture, it took 3 potassium hydroxides to react with it. The molar mass of potassium hydroxide is given here. Now let's set up the problem to solve. So for the crystal light, there were 12 milliliters, so 0.12 grams of potassium hydroxide. And now everywhere you see X in my solving strategy, it's going to be potassium hydroxide. So the first step, it says 1 mole of potassium hydroxide over the molar mass of potassium hydroxide, which is given 56 grams of potassium hydroxide. And then the next step, on the top, we'll have moles of our Y substance, which we're trying to find out citric acid. I'm just going to abbreviate citric acid because I can't fit all the formula on there. And then on the bottom, I'll have moles of potassium hydroxide. Now, how many of each? The question marks come from the balanced reaction equation. There's 1 citric acid, and there are 3 potassium hydroxides. The last step, the Y substance now, our citric acid, the molar mass we calculated. So on top, 192 grams of citric acid, and on the bottom, 1 mole of citric acid. Now the reason that it's set up this way is so that units cancel. Anything on the top and bottom of a fraction, anything divided by itself, reduces to 1 and just factors out. So I can factor out these unit labels and show that the one that's left is the one that I'm looking for in my problem. How much citric acid is what I'm trying to find out, and that's what I'm going to end up with when I do the calculation. So to do the math, multiply across the top and write it down. So 0.12 times 1 times 1 times 192. I'll write down 23.04. And on the bottom, 56 times 3 times 1. Oops, how did I get a 0? 56 times 3 times 1 is 168. And then the top divided by the bottom. 23.04 divided by 168 equals 0.137 grams of citric acid. That's how many grams of citric acid were in the crystal light. So if it took more of the potassium hydroxide to react with the citric acid in crystal light than it took to do the great value titration, this one only took 0.08 grams of potassium hydroxide, then when you do the next calculation yourself, you should predict if the answer is going to be larger or smaller than the one that we just got here. What do you think is going to happen? if it takes less potassium hydroxide, but you're doing the same calculation, if you start with a smaller number, you should end up with a smaller answer. It looks like the great value isn't as sour as the Crystal Light is. So if sour is your thing, then you want Crystal Light, the name brand. But if value is your thing, then go for the Walmart Great Value brand. They probably both taste just as good, but I haven't done the taste test. I'm just a simple chemist, and all I'm interested in is the mass. Alright, so tomorrow we're going to have an assessment. I'll give you a similar problem where you'll have to do a titration at the lab bench to find out how much of a material is in a mixture and answer some questions about the titration process.